Now, we have finally reached our climax. In this video, we're gonna give an intuitive proof of the second fundamental theorem of calculus, and then we'll cover the first fundamental theorem of calculus in the next one. Let us use the same setup as before. Suppose you were running north along State Street. Then we can define a position function as t, which gives us how far up north you are at time t. If we take its derivative with respect to t, then we get a velocity function. For every t, vt gives us your instantaneous velocity at t. So the relationship between velocity and position is that velocity is a derivative of position, whereas position is an antiderivative of velocity. Everything we said in these videos is gonna hold for any pair of function s and v, such that v is the derivative of s, or equivalently, s is an antiderivative of v. So when you have to work with an arbitrary function f and its derivative, you can still think of f as a position function and its derivative as a velocity function, and then use the intuition we discussed here. There's nothing magical about position and velocity in particular. All these statements are going to be transferable to any pair of derivative and antiderivative. Alright, so now with that out of the way, let us get to our climax, the fundamental theorems of calculus. Let's see what the hype's about, okay? Within our setup, we can say that the first fundamental theorem of calculus is about position, and the second fundamental theorem of calculus is about displacement. Both give an alternative way of thinking about area under the curve of a given velocity function. You see, while the geometrical manifestation of derivatives is slope, the geometrical manifestation of integrals are areas. So here are what the theorem said in plain English. It's actually easier to start with the second fundamental theorem, so let's do that. So let us fix some nice continuous velocity function. And let us pick two times, say 5 and 7, but you could replace this with any a and b. Then we can consider the area under the graph of the velocity function lying between 5 and 7. Or if you want to be more pedantic, the area that is bounded by the curve y equals to v, the x-axis, and the vertical line t equals to 5 and t equals to 7. But for simplicity, from now on I will just say the area under the curve y equals to v between 5 and 7. Okay, so what about that area? Well, the second fundamental theorem of calculus said that this area turned out to be exactly equal to your total displacement between 5 and 7 a.m. Well, it means the difference between your position at 7 a.m. and your position at 5 a.m. For example, if at 5 a.m. you were at 0 north and at 7 a.m. you were at 800 north, then your total displacement between 5 and 7 a.m. is gonna be 800 miles. Now, you're probably wondering, can we just say total distance traveled instead of total displacement? Well, you can, but only if the velocity is always positive. In general, there is a subtle difference between displacement and distance traveled. If at 5 a.m. you start at some point and then keep moving forward, then your total distance traveled is indeed equal to your displacement. It's just gonna be the difference between your position at 7 a.m. and your position at 5 a.m. So when are they not the same? Well, imagine that at 5 a.m. you start here and then you run forward a little bit. But then you suddenly realize that you need to pee, so you had to run back home at the starting position. And that happens to be exactly where you end up at 7 a.m. In that case, your total distance traveled was bigger than 0. You did indeed have some workout, but your total displacement is only 0 because you end up at the same place where you stopped. That is, s of 7 is exactly equal to s of 5. A possible picture for this situation is as follows. For simplicity, let's suppose that before you needed to pee, you were running with constant speed of 3 miles per hour. I guess running here is in quotation mark. So you keep that same speed all the way until 6 a.m., where you suddenly realize that you needed to pee, so you run back home with the same speed. Now, since you are running in the opposite direction, your velocity would be minus 3 miles per hour. Remember, that's the difference between velocity and speed. Velocity also includes information about direction. Alright, so let's see what the second fundamental theorem of calculus says in this case. Let's see what the right-hand side should be. Well, it should be your total displacement. And what's your total displacement? We don't actually even need to know your position at 5 and 7 to find this total displacement. If you run forward for an hour and then run backward for an hour with the same speed, then you must have ended up at exactly the same location that you started with. And so your total displacement should be 0. Now, let us check to see if the left-hand side is also 0. Alright, so what's on the left-hand side? Well, the left-hand side is about the signed area under the graph of the velocity function, right, between 5 and 7. Now, what is signed area? If we drop the word sign and only ask about area, then we see that the area of this rectangle here is 3 times 1, which is 3. And so is the area of this rectangle. However, while the signed area of the first rectangle is still 3, the signed area of the second rectangle is actually minus 3. When we compute signed area, we need to put a minus sign in front of the area of any region that lies below the x-axis. Thus, what is the total signed area under the curve between 5 and 7? Well, that's just going to be 3 plus with minus 3, which is 0. So we see that in our picture here, the sign area is exactly equal to the total displacement. That is promising. It seems like the theorem is true. Now, let me show you that this example wasn't a fluke, and that intuitively, this theorem is actually obviously true. To that end, let us start small and prove the theorem for the easiest case, the case of constant velocity. Let us suppose now that you didn't need to run home to pee, and the whole time between 5 and 7 a.m., you were just running with constant velocity, 3 miles per hour. What would your total displacement be in that case? Observe that you don't really need to know your position at 5 a.m. or your position at 7 a.m. to answer this. Between 5 and 7 a.m., there were 2 hours. Since your velocity was constantly 3 miles per hour, that means each hour you move forward by 3 miles. So after 2 hours, you should have moved forward 3 times 2, which is 6 miles. Thus, since you were running with constant velocity, your total displacement is just equal to velocity times duration, which is 6 miles. But now observe that this is just the area of this rectangle. Observe that the height of this rectangle is just your velocity, which was 3 miles, and the width of this rectangle is just the duration traveled. So the area of this rectangle is just going to be equal to the height times width, which is velocity times duration, which is exactly equal to the distance traveled. In this case, that's the same as total displacement since you did not change direction. Now, observe that there is nothing magical about this velocity 3 miles per hour or about this time 5 and 7. The same argument works for any constant velocity. That is, if you know that over some time interval delta t, your velocity was constant, then you know that your total displacement is just going to be equal to the total distance traveled, which is just velocity multiplied with duration traveled. But this is just exactly the area under the graph of velocity function over your time interval. That is because over this time interval, since you have constant velocity, your velocity function is just going to be a horizontal line. And thus, the area under it is just the area of a rectangle whose height is the velocity and whose width is the duration traveled. Thus, this area is going to be exactly equal to the total displacement. So we see that the second fundamental theorem holds at least for the case of constant velocity. But then, it must hold in general, even when the velocity is not constant. Because over a small enough time interval, your velocity is almost constant. So let me explain. Now, even though your velocity might not be constant, over a really small interval, your velocity is going to be almost constant. If you check your speedometer at 5 a.m. and see 3 miles per hour, and then I ask you, what's your speed at 5.00000001 a.m.? It would be safe for you to say approximately 3 miles per hour, right? Because even though it might not be exactly the same, it would not have changed too much during such a short time interval if we're assuming that the velocity function is continuous, at least almost everywhere. Okay, so during a really small time interval, your velocity is going to be almost constant. For example, over this tiny time interval, your velocity will be almost constantly equal to the velocity at 5. Thus, by our previous discussion, we see that your total displacement during this tiny time interval is going to be approximately equal to the area of this rectangle here. Now, since in this drawing, the velocity is always positive, total distance traveled and total displacement will mean the same thing. So I will be using the term total distance traveled instead since it's more intuitive, but do keep that in mind. Alright, so we can repeat the argument that we just made to show that the total distance traveled is always going to be equal to the area under the curve, even if the velocity function is not constant. The idea is just to divide the time travel into really small interval. Now, over each such tiny time interval, the velocity is approximately constant. For example, over this time interval here, the velocity here, the velocity is almost approximately equal to the velocity at this point in time here. So we can think of the graph as approximately horizontal over this tiny time interval. Thus, from our previous discussion, we know that the total distance traveled during this tiny time interval here is gonna be approximately equal to the area of this rectangle. Now, this holds for all of this tiny time interval, so you can add them all up. And you see that the total distance you have traveled between 5 and 7 a.m. is just going to be approximately equal to the sum of the area of this rectangle, right? So from 5 to this time, you have traveled this much. And then from this time to this point in time, you've traveled roughly this much. So you keep adding it until you get all of the rectangles. This is an approximation, of course, but the smaller you make the time interval, the better of an approximation it's gonna be. Now, when the intervals become infinitely small, that is, think of it as the interval shrink to a point, or as the non-standard analysts say it, when the interval has infinitesimal length, then the approximation is most accurate. It's actually gonna be an equality. And the total distance traveled is actually gonna be equal to the sum of the area of the rectangles. But when these intervals become tiny, when they shrink to a point, then these rectangles will just shrink to a line segment like this. And so they would actually fill this whole area. So the sum of the area of these rectangles will actually be this full area. And thus the total distance traveled is actually equal to this area here under the curve, which is exactly what the second fundamental theorem of calculus says. Alright, so that's the quote-unquote proof of the second fundamental theorem of calculus. Before we end, let us do a quick recap. The second fundamental theorem of calculus said that the total displacement between 2 points in time is always going to be equal to the signed area under the graph of the velocity function between those two times. Now this is obvious when the velocity function is constant, because in that case the total displacement is just going to be equal to velocity times duration travel. And that's just exactly the area under the curve. Now, for the general case, when velocity is not necessarily constant, we can just divide our travel time into tiny time interval over which the velocity is almost constant. Actually, if we make them small enough, say if we make them the duration of a moment, a single moment, whatever that means, then the velocity over such interval will be constant. And so, from the previous argument, we see that the total distance traveled or the total displacement over each such moment is just going to be equal to the area under the curve over such moment. And if we add those all up, we see that the total distance traveled or total displacement must be equal to the full area under the curve, which is what the second fundamental theorem of calculus says. Alright, so that's the second fundamental theorem of calculus, which was about area versus displacement. Next up, we're going to talk about the first fundamental theorem of calculus, which will relate area with position.